Another light management factor is the absorption of the substrate. Absorption is a good way to reveal the effect of light scattering. As you can see from the graph below, there are AR0 and AR1. AR0 stands for silicon nitride coated silicon nanowire array, as the optimal geometric figure we figured out in the previous section. W equals to 250 nanometers, H equal to 100 nanometers, and thickness equal to 60 nanometers. However, we alternate S, which is the thickness of a substrate arythal, to show you the variation. And then AR1 equal to single silicon nitride thin film of 18 nanometers. We also plotted that as a reference. As you can see from the graph, AR0 has better absorbance than AR1. And then, as you can see, when the wavelength increases, the absorbance is getting better. However, our technology now is making the substrate smaller and smaller, so we look from the thickness. As S decreases, the absorbance also decreases. And when the S equal to 1 micrometer, you can see that there's a very obvious difference between the AR0 and AR1. I think right here. The next element of light management is light trapping. So, only light with wavelength over 800 nanometer can penetrate the silicon substrate with 100 micrometer thickness. So, 800 to 1000 nanometers are the major concerns. Below figures show the calculated normalized scattering intensity at different scattering angles. When the incident light is vertical to the front surface, the scattering angle of the first non-zero order light can be described as the below equation. N is the refractive index of silicon, T is the period of AR0. As we recall, AR0 is silicon nitride coated silicon nanowire array. The scattering efficiency is defined as the total propagation of all non-zero order lights, and it shows the ability to change the light into oblique propagation direction. So as you can see, the below graph, it's the scattering efficiency of AR0 in 800 nanometer to 1100 nanometer. Scattering efficiency generally declines as the wavelength increases. However, the minimum value is still over 50%. It means that more than half of the transmitted light would propagate in non-vertical direction. Some of the existing silicon solar cells can actually achieve total internal reflectance. For example, the PERC cells, the passivated emitter and Lear cell, have achieved total internal reflectance through back surface smoothing and silicon dioxide passivation. The below equation describes the total internal reflectance for these types of cells. N0 is the refractive index of silicon dioxide, and beta is the critical angle when total internal reflectance can be achieved. So, using the previous formula and looking back to the original formula, when when alpha is greater than beta, total internal reflectance of all non-zero order light may be achieved. This gives us the below equations. Lambda is greater than N0 T. For N0 equal to 1.46 and T equal to 600 nanometers, lambda is greater than 876 nanometers. What does it mean? It means that only lights with wavelength greater than 800 nanometer can penetrate a 100 micrometer silicon substrate. Therefore, we've got the lambda as 876. It proves that silicon dioxide passivation at the back surface can obtain nearly total internal reflectance for all non-zero mode of lights. So after the front surface scattering, the light will travel through the substrate and reach the back interface. And light trapping is very high internal reflectance at the back interface. As you can see from the graph, AR0 is still silicon nitride coated silicon nanowire array. The black line is at 1100 nanometers, the red line is at 900 nanometers, and the single silicon nitride thin film is AR1 at 1100 nanometers. So as you can see, the critical angle is at 16 degrees, because after 16 degrees, all three of them improves by a lot. However, AR1 actually outperforms AR0. AR1 can reach to 100%, if AR0 can only reach around 90. So isn't AR1 better than AR0? No. Actually, silicon nitride coated silicon nanowire array has high internal reflectance for zero order mode lights. The graph before shows non-zero order. So for the zero order one, silicon nitride coated silicon nanowire array actually has 58% at 1100 nanometers, while single silicon nitride thin film is only at 15%. Silicon nitride coated silicon nanowire array has low external surface reflectance and high internal reflectance. These two are the important measures for light trapping. Furthermore, the zero-order light will be partially coupled into high orders after internal reflectance at the front interface, which means that after it's been coupled, there are more lights for the silicon nitride coated silicon nanowire array to use. So when you look at everything together, actually silicon nitride coated silicon nanowire arrays perform better than single silicon nitride thin film. So in conclusion, silicon nitride coated silicon nanowire array has achieved ultra-low surface reflectance with appropriate parameters: T equal to 60 nanometers, W equal to 250 nanometers, and H equal to 100 nanometers. And optimized average reflectance can reach around 1.6% at air mass 1.5 spectra. On the other hand, it has good scattering effect, which lead to extra absorption at the substrate. Furthermore, it also has good light trapping capability around 90%. From all the data shown above, before, it shows that silicon nitride coated silicon nanowire array is very good at improving light management of silicon cell solar power.